On our second lesson, we're going to see the difference between speed and velocity. Similar to distance and displacement, speed and velocity, they are very closely linked, but they are going to be different. You already guessed it. Speed, one of them is going to be a scalar, which is speed, and the other one is going to be a vector, which is the velocity. We're still going to use the example I mentioned in the previous lesson, the example of Joe's motion. And we are going to build on what we did last lesson to talk about speed and velocity and the difference between them. So what are we going to do here? First, we're going to remember what you learned in previous years, which is every time you have a distance time graph or a displacement time graph, you can get the value of the speed or the velocity by doing the gradient. So the gradient of these lines would give us those quantities. For the distance time graph, which is a scalar, you would have out of the gradient, you would have the speed. From the displacement time graph, if you get the gradients, you will get the velocity. How do you get gradients? The change of height over the change in distance. That's what I did already. So here, the speed from A to B is going to be the distance A to B over the time A to B, which is basically the gradient over here. This divided by that, which is 5 meters per second. If you do it for the section BC, obviously, it's also going to be 5 meters per second because the inclination of the line is the same. As you saw in the text, Joe is always moving at the same pace, meaning that the speed is always going to be the same. In real life, this never happens. Before you change direction, your speed needs to go to 0, but this is just to illustrate a point. It's not a real life situation. It's a very rough model of how people move. What about the displacement? The displacement, you had a negative inclination before. Here it is. No, here it is. So this means that you have a negative gradient. The negative gradient is going to be the value of the velocity for this section BC. I calculated it like any other gradient, and I have for the first section 5 meters per second from A to B when Joe was moving in that direction, and minus 5 meters per second on the second section when he was moving in this direction from B to C. So how do you draw the graphs? For the speed time graph, it's going to be a straight line. Every time you have a speed time graph with a straight line, this obviously means constant speed. You will also have constant lines for the velocity time graph, but in this case, you have a straight line that is negative, which corresponds to the second section. This can never happen on a speed time graph because it's a scalar, and you cannot get negative values on a scalar. You will always have positive values over here. So, see the contrast on the two? The speed time graph and the velocity time graph. You can see these A's over here. You remember probably from previous years that every time you have a speed time graph or a velocity time graph, it's likely that you are more used to the speed time graphs. The area under the line on a speed time graph would give you the distance traveled. Remember, this continues being the case, obviously. The area of a speed time graph gives us the distance, but the area of a velocity time graph gives us what? It gives us the displacement, obviously, right? In this case, you only have a rectangle, so you do the base times the height, and you would have the total of 70 meters. But here you have two rectangles, one of which is a negative rectangle, all right? So if you just apply the values that you have here on the scales of the graph, you would have for the first rectangle a positive number, but for the second rectangle, this would be minus 5 times 14, and added up to the value that you get over here, you would have the total displacement that we already saw on our previous lesson of 30 meters per second. So again, the best thing that can happen to you every time you solve kinematics questions in mechanics is having a velocity time graph, because a lot can be taken, a lot of information can be taken either directly or through calculations from this. Directly, you have the velocities at every single moment. Indirectly, you can get the acceleration. In this case, the acceleration is going to be zero, but as we're going to see, we can get the acceleration out of the gradient and the displacement out of the area. So everything that you'll need to know about the motion of something can be taken from a velocity time graph. One last thing to talk about, which is the average speed or the average velocity. This is probably one of the first things that you've learned in physics back then. The average speed is the total distance divided by the total time. So in this case, you have a total distance of, what was it? It was 70 meters divided by the total time. No, 170 meters divided by the total time, which is obviously 5 meters per second. There was no change over there. So if this is the speed throughout as time passes, the average is obviously going to be the same. But the average velocity is what? Is the total displacement divided by the total time. And the total displacement is just 30 meters per second. The time is the same, which gives you a value that is completely different, as you can see over there.